to the third talk of my video lecture series for NAS. So today we'll be discussing about relativistic scalar fields, and this will be the first part of this topic. Because of the length of the topic, I decided to break it down in 2 or more segments. So we will mostly go through the introduction and the initial treatment of relativistic scalar fields today. So to begin with, let's recap a little bit of what we have learned till now in the first 2 lectures. So quantum systems with variable particle numbers or even infinite particle numbers cannot be defined in a Hilbert space. What does it mean? That if you have a scenario where particles are being created or absorbed, or you have infinite number of particles, it is difficult to assign wave functions to all of them or assign wave function to the system in a convenient way, because usually we know that wave function depends on space and time coordinates, and because the particle number is not fixed or finite, that assignment is practically not possible. So the concept of wave function needs some modification, and we either can stick with it with all these problems, or we can altogether let it go and go to a different picture of quantum mechanics, which is known as the Heisenberg picture, where operators represents the state and dynamics, everything regarding the system, and those operators evolve according to space and time. The corresponding so-called wave function does not evolve in space or time, and usually it represents a standard state of the system, which is called vacuum, or you can say it's a state of the system where no particles are present, and rest evolution of the system is represented through the evolution of the operators. Such a space becomes useful when you define something called raising or lowering operators. I guess everybody is familiar with Heisenberg operators or the harmonic oscillator systems, where you have these A and A dagger operators, which actually are also known as the raising and lowering operators, which takes you from one state to the other, and with respect to a vacuum or ground state, and that ground state has some real energy, which is denoted as V. It can be 0, but it's a semi-positive definite quantity. It can be either positive or 0. And such a structure, A dagger A kind of a structure, assures that this system is solvable, that we know from the elementary treatment of harmonic oscillator. And on principle, one can create infinite number of states in that system, and each state represents certain number of excitations of the harmonic oscillator. But this definition is actually general. We can have any system where we can define some annihilation operator A or some creation operator A dagger. It does not need to be of the same form as the harmonic oscillator. For any A and A dagger existing, we can have these infinite Hilbert space, and this will serve our purpose. And in this regard, what happened that if you have a many body operator, say eta, which can be a linear combination of single particle operators in general, that is adequately represented by a operator in this new space, which is known as the Fock space, where the whole operator is constructed in terms of this raising and lowering operators corresponding to certain other parameters represented by these eta mn coefficients, and they can have infinite values, these m and n coefficients, going from 1 to say infinity. So in the left hand side, if you see, the many body operators are only the operators, but in the, sorry, oh, excuse me, yeah. But in the right hand side, you can see that we have this creation and annihilation operator and the coefficients eta mn also. So it's a more general prescription that we have discussed in the previous lectures. Now, because you have these creation and annihilation operators, you can combine them in any arbitrary way. And if that combination does not follow the A dagger A kind of structure, there is no analog in the many body space of that structure. But in the Fock space, you can define a physical process which corresponds to this, say, A dagger A kind of structure that we see as quantum corrections in high energy physics or some complicated Feynman diagrams. All those kind of effects which are not seen in single particle quantum mechanics are represented by such combinations. Okay, so the point is that in this new representation, as we discussed before, that states themselves they correspond to operators in the Fock space, and that's why it is called a second quantization. Another way to look at this second quantization is that you consider a continuum system classically, which is represented by a field that you know, like a classical field. It can be an electric field, magnetic field, or a density field, whatever, which depends on position x and time t. One thing is to notice is that in this description itself, somehow space and time are already in the same footing as independent variables for this field, just to keep it in mind. And we can always expand this field in a single particle basis where psi and x are single particle wave functions, and it will have some coefficients, these ans. Now, if we upgrade these ans to operators, then this is called field quantization. How it is, it can be a second quantization. Well, if the psi is a probability distribution of quantum mechanics in the Schrodinger picture, then upgrading these ans to again to operators means you are quantizing again, because in quantum mechanics we know a wave function is just a function, although its interpretation makes it quantum, that it's a probability distribution, but it is a function. Now, if we upgrade its coefficients to operator, it gets quantized again, and that's why this field quantization is equivalent to second quantization. So these are two different approaches, and the easiest one I find to be the field quantization, because you have a field that behaves classically. It's a function, and you just quantize its expansion coefficients. Okay, so after knowing that, let's now talk about relativistic scalar fields. So we have a scalar field that can be very well be this psi. We don't bother what its physical interpretation is. It can be a wave function or anything else. But the thing to note is that space and time are at equal footing. So although the system does not have any covariant structure, this whole approach is suitable for covariant treatment. In the last lecture, we talked about the Schrodinger field theory, and we have seen that it's a non-relativistic field theory. So this field description can accommodate non-relativistic structures also. today we will go to the relativistic counterpart. And to do so, we notice one thing, that after this, these expansion coefficients ANs are quantized, we can construct operators in the new space. You can call it a Fock space, where the effects, all the effects that can be constructed in this Fock space may not have counterpart in the Hilbert space. So that means that we can talk about processes in Hilbert space, in Fock space, which are absent in first quantized theories. And as we discussed before, things like particle creation, annihilation, etc., and etc., those kind of processes, and loop effects, quantum pair production and annihilation, such kind of processes cannot be handled in a first quantized description or in a Hilbert space, but in Fock space they are naturally treated. So before going into relativistic scalar fields, we need the notations. So in special relativity, you have something called a metric operator. Okay, this description is general for general relativity, also for any kind of curvature included. So for this particular case, we are talking about a flat space. So we have a diagonal metric where denoted by the G mu nu tensor. Mu and nu can take d+1 values in a d-dimension space. The zero index corresponds to time. Like our space time is 4+1 dimensional, that is the Minkowski, we know. And there are covariant and contravariant counterpart, and they contract accordingly this rule, which gives you a Konecker delta. Now we can define a covariant vector. It's a d+1 dimensional vector. If you consider d to be 3, we have a 3+1 dimensional space, our actual physical space that we see in our day-to-day life. And therein, this contravariant vector means the time variable. It's a position vector. It corresponds to the time variable and the position vector, free position vector. Okay. And the index stays as a suffix. So equivalently, you can construct a covariant operator where this variable stays in downstairs, and it's basically the time and the negative of the position vector. Now these covariant and contravariant vectors are connected to each other through the metric tensor, through contraction of repeated indices, which is the Einstein summation convention. And for a contraction, one index has to be down, the other index has to be up. That is the only rule. Okay. One second. Okay. So now you can define covariant and contravariant derivatives. So these derivatives, the time component is the time derivative, and the space component for the contravariant partial derivative is the negative of the gradient operator, where for covariant partial derivative, the space part is the positive of the gradient operator. So you can see the position and derivative, they behave oppositely in the space part, and they have to do that to be consistent, because the space derivative has the space coordinate in the denominator. So from these definitions, one can construct a scalar product. The scalar product between two 4 vectors A and B is basically the product of time components minus the dot product of the space components. Then you can define a generalization to the Laplacian operator, which is the dA Lambertian, which is defined like this. It's a contraction of the partial derivatives, and this amounts to the time derivative square minus the Laplacian. But the divergence operator, divergence of any divergence of any 4 vector A, does not have this minus sign. It is a time derivative of the time component plus the divergence of the space component of the 4 vector. Okay, we will follow these notations because we are going to talk about a relativistic scalar field. So the scalar field, physically what it means, it is some defined amplitudes across the space. You can talk about these water waves, a snapshot of these water waves, they are not moving. So the height of the water wave from its undisturbed surface can be considered to be the amplitude of the field, and which is different in different point in the space. So it represents a scalar field. So one might ask, what is a vector field? So for example, look at this paddy field. So not only the height individually, but there is a notion of direction also, that each blade of grass, which way it is pointing, that is also important. So this can be considered as a vector field. There can be tensor fields also. The point is that it is very difficult to show tensor fields. So this is one example of stress tensor field over a spherical surface. So the red arrows corresponds to the stress vector going in, component of the normal stress tensor, and the blue ones are the components of the tangential stress tensor part. So there are at least 2 directions at each and every point. So this is kind of a partial pictorial description, but it's usually difficult to visualize. But it essentially means that you have a field distribution where at each point there are more than one direction. At least there are 2 directions involved at each point. And it's a second tensor field. You can go up and above. There can be many directions at the same point, representing each component of the tensor. So this concept can be generalized. Now the relativistic scalar field means the dynamics of the scalar field represents a relativistic symmetry. Sorry. So in this case, you can see the dynamical equation corresponds to a scalar field phi. M stands for mass, and this DLM version, which we have just seen that it has a covariant structure. So this equation is a relativistic equation, covariant equation. And this is the simplest form you can have. And maybe you can put M is equal to 0 to have a massless scalar field. And it's a second derivative in time and space also. So it satisfies the minimum qualification to be a dynamical equation. And this is the simplest relativistic equation, which represents a relativistic scalar field known as the Klein-Gordon equation. Now this equation can be derived from a Lagrangian, corresponding Lagrangian, which is a function of the field phi and its 4 derivative, because mu stands from 0, 1, 2 up to 3. And this is the form of the Lagrangian, which when you consider the Lagrange equation of motion, if you plug this Lagrangian L into there, you will get back the Klein-Gordon equation. Now the corresponding Hamiltonian comes from the Legendre transformation of the Lagrangian density, leading to the Hamiltonian, which is the integrand here. Here the partial derivative of the Lagrangian with respect to the time derivative of phi gives you the canonical momentum corresponding to the field phi. So this is just the Legendre transformation. And once performing the Legendre transformation with this Lagrangian, this Klein-Gordon Lagrangian, you end up with the Hamiltonian that looks like this expression. And from there, using the Hamilton's equation, which is given like this, where this pi stands for the conjugate momenta of the scalar field, which is the partial derivative of L with respect to time derivative of phi. If you take one more time derivative represented by this dot, you can get the Heisenberg equation, and that will just reproduce the Klein-Gordon equation again. Now, up till here, if you construct the Lagrangian and Hamiltonian, it's still classical. And our goal is to finally quantize the theory to achieve second quantization or field quantization. We already have the field phi, which can be interpreted as some collective wave function of the system, and we want to quantize it more to represent it in a Fock space. So we first consider a single particle state, which is just, we are calling it single particle just because there is a definite momentum, which is just an exponential function, and corresponding considering the dot product in 4 dimension, covariant dot product, we see that it depends on k naught. K naught is the fourth component of the momentum, which is actually energy of the system, and the momentum vector k, which is defined like this. Because it has a definite momentum, it's a single particle state, and you can readily see that if we go back to the Klein-Gordon equation, this single particle state easily solves the Klein-Gordon equation following the relativistic relation between energy and momentum. And correspondingly, you can define a single particle Hamiltonian also, which just looks like this, which is the Laplacian square negative plus m square, that is the square of the single particle Hamiltonian. Now the point is that because this single particle state solves the Klein-Gordon equation, any general state can be expressed as a linear combination of these single particle states. Now this UKX is the single particle states, and these phi tilde are some coefficients, and mathematically it is just a d plus 1 dimensional, or d being 3, it is 4 dimensional. It's a Fourier transform, nothing more than that. So phi tilde are equivalently the Fourier transform of the wave function phi. This red quantity is just the normalization factor that appears in front of any Fourier transform. So now, because one can see that that the single particle wave function satisfies the Klein-Gordon equation, which essentially will give you something like this, that and also the it says that the k square has to be equal to m square. This Fourier expansion of the wave function is valid only if the Fourier transform has a delta function dependence. It's a Dirac delta function dependence, which actually is 0 unless k square is equal to m square when it is infinity. So this phi tilde has to have a dependence on this Dirac delta function and some other dependence on momenta for momentum k mu. The reason being that when you put this phi x into the Klein-Gordon equation, it should give you 0, right? So usually if you put ukx, it just gives you minus k square plus m square, that we have seen. So to make it vanish at k square is equal to m square only, you put a Dirac delta function. Okay. So this condition that k square has to be equal to m square is called on-shell dynamics. That is the relativistic dispersion equation. But why we are saying it's a special case? The reason being that the principle of superposition or the Fourier expansion requires an integration over all the possible momentum. And these on-shell dynamics or relativistic dispersion corresponds to one particular value of the momentum. So because of that, this introduction of Dirac delta is a must. So the solution space is just a hyperbolic surface in the d plus one dimensional space with a constraint which is the relativistic dispersion, and that is called the on-cell surface. And the rest of the space is called off-cell accordingly. So now these Dirac delta function, which contains k square and m square, it can be broken down into the linear variables k naught and ek. Ek is the energy of the relativistic particle, single particle, and this is the formula for the expansion, which can be found in any standard textbook of quantum field theory. Now, after putting back that expression for Dirac delta into the expansion of the Klein-Gordon field, will finally leaves us with this expression where we have this k tilde to be a little bit different than k, where k naught had where k had the time component to be one second. Yeah, so k naught had the time component to be e. Here you can see the k naught was plus minus e, but for k tilde naught is ek. So ek is the energy with momentum k. So ek is dependent on k. So this k tilde actually have only three variables here. That's or in d dimension it has the d number of variables, and k naught has been integrated out. So ek now is always on shell. It is the energy of the particle with momentum k. Earlier, this E and K were totally independent. E was an independent component of the four momentum, but now this Ek is dependent on K. So finally, we have a situation where the energy of the system, which is Ek, is always positive. It has a definite value because energy depends on K square. K is the three momentum. And it is always on cell. That means it will be always on cell, and we are limited to the d-dimensional hyper surface of a d-sphere. So the energy cannot be negative, and thus we have a bounded spectrum. Minimum energy can be zero on principle. Okay. So these operators like a, which are dependent on k tilde plus minus k tilde, they now act on a space which is infinite dimensional. Why infinite dimensional? Because still we have an infinite integral over k, and each of them are leveled by the space momentum k, which is a signature of the Fock space, and they all represent a scalar field which lives in a Hilbert space. So this is a transition from Hilbert space to Fock space. So it is equivalent to a second quantization. Now we can put some more conditions. We can demand the scalar field to be real. If the scalar field is real, then this a minus k tilde operator has to be equal to the complex conjugate of the a k tilde operator. So if it is the case, then finally the scalar field looks like this. It is just a linear combination of ak and ak stars, which is a real combination. And here we, for brevity, we have just scaled the a k tilde operator to this a k operator. It's just a redefinition by absorbing a root over ek in the denominator. So we end up with this measure, which is a very standard measure. It is just for convenience. And from there, one can find the conjugate momentum for scalar field, which looks like this. This is an expression. And mind you that in the conjugate momentum, this energy of individual momentum that comes out as a factor because you take a time derivative. And this integration index KD is just the integration with this measure denoted by color red upstairs. So we can actually reverse these operators, AK operators, in terms of the scalar field and its conjugate field pi, like this. So these are the expressions one can check. And all these calculations I mostly follow from this reference, which is Lectures on Quantum Field Theory by Professor Sogdas, and this is the page number. So now, because we can interchange between this scalar field and the creation and these AK and AK star operators, you can write down the Hamiltonian in terms of that. The Hamiltonian we obtained at the beginning through Legendre transformation. You can write down the Hamiltonian in terms of these AK and AK star operators, and which has this particular form. Now you can automatically see that this EK, the energy, comes out in the front like this. So it kind of keep tracks of individual energy of the particle with momentum k. Then this AK and AK star, or AK star and AK, keep tracks of this individual particle with momentum k. Now at this level, our ground state or the vacuum where there are no particles, it will have zero energy, but it cannot have negative energy. All the energy states, there are infinitely many of them, are towering above the ground state. So we have a positive definite system. There are no negative energies, and it is in a basis of individual free particles. So this is the version of the relativistic free particle Hamiltonian in terms of individual Fock space operators. Now, to achieve complete quantization, we have to upgrade this A and A star quantities to proper operators, or we have to define some quantization condition between them, namely something like this. Once we do that, the second quantization is complete. And you can notice this is the harmonic oscillator quantization condition, nothing more to it. And once you do that, what happens that when you pass through A and A star, there will be a non-zero number, which is the Dirac delta function here. And because of that, this Hamiltonian will correspond to a ground state energy which is non-zero, akin to what we have in harmonic oscillator. And A star will be upgraded to A dagger because it will be an operator, and that will mean this whole structure A star will look like A dagger, and we know that that is the square integrable structure. So this Hamiltonian will be solvable, and we can express everything regarding the scalar field in terms of these creation and annihilation operators. And that will be the topic for the next lecture. So hope to see you all again, and thank you for listening.